Chapter 19 will focus on aldehydes and ketones. Both functional groups are very similar. They both contain a carbonyl, but the difference is aldehydes have an H directly attached to the carbonyl, whereas the ketone is surrounded by two carbon groups. In this video, we will go over naming aldehydes and ketones, preparing aldehydes and ketones, which will be a review of reactions we've learned previously. We'll talk about the properties of aldehydes and ketones, as well as the general mechanisms for nucleophilic addition reactions. Naming aldehydes is similar to the rules that we've learned for naming with previous functional groups. First, we're going to identify the longest chain of carbons. We want to make sure the aldehyde is included in the longest chain. So we'll go ahead and take a look at the longest chain of carbons. We have 1, 2, 3, 4, 5, 6. Just to make sure there's no other possibilities, 1, 2, 3, 4, 5. So we have 6 carbons as our longest chain. Next, we want to number the longest chain, giving number 1 to the aldehyde. So I'm going to start on the right, and I will number my 6 carbons, like that. Now we'll go ahead and follow previous rules. We will put the branches in alphabetical order and also indicate what carbon those branches are on. And then we will name the parent chain. So we have a methyl group on carbon 5. We have an ethyl group on carbon 3. So in alphabetical order, we have 3-ethyl, 5-methyl, and then to name our chain, we have a 6-carbon chain, which is going to use the prefix hex. And typically a 6-carbon chain would be hexane. Instead, we're going to remove the E and replace it with Al, so we get hexanol. Okay, so Al is the suffix we use when writing about an aldehyde. We want to be very careful and not mix it up with Ol, because Ol would indicate an alcohol. There are a few aldehydes with common names that you should be familiar with. This one is the simplest type of aldehyde, where we have a carbonyl attached to 2 hydrogens, and this is known as formaldehyde. When you have an aldehyde attached to a methyl group, it's known as acetaldehyde. And an aldehyde directly connected to a benzene ring is known as benzaldehyde. With naming ketones, we will also identify the longest chain of carbons, making sure to include the ketone functional group. Next, we will number the longest chain, giving the ketone the lowest possible number. Finally, we will name the ketone, and for the parent chain suffix, we will use one, O-N-E. We also have to include the location of the ketone functional group. Now, this was not necessary with aldehydes because aldehydes were always on carbon number 1. So with our first example, we will number our longest chain. Now, this chain has 7 carbons. If we were to start counting from the left, our ketone would end up on carbon 1, 2, 3, 4, 5. But if we start counting from the right, it will end up on carbon number 3. Now we want to focus on giving the ketone the lowest possible number, so we will start counting from the right. Now the prefix for a 7-carbon chain is heptane. There are 2 ways that we can name this molecule. We can either name it as 3-heptanone. The 3 is indicating the location of the ketone. The heptane means that we have our 7-carbon chain, and the one means that we're working with a ketone. Or we can write it as heptane without the E, 3-one. Either way is an appropriate way to name this molecule. Now in our second example, we have a ketone with a few branches. Now when it comes to numbering this ketone, again, we want to focus on giving the ketone the lowest possible number. So if we start counting from the left, we have 1, 2, 3. Our ketone will end up on carbon number 3. If we were to start counting from the right, 1, 2, 3, 4, it would end up on carbon number 4. Since our ketone is the priority, we're going to start counting from the left. Now we will name our branches. We have a hydroxy group on carbon number 5 and a methyl group on carbon number 4. So in alphabetical order, the hydroxy group goes first. So we have 5-hydroxy, 4-methyl, and then placing the location of our ketone is at carbon number 3, and hexanone is going to be our parent chain name. We could also rewrite the end to have it as hexane 3-one. We've already learned several ways to prepare aldehydes and ketones from previous chapters, so all of these reactions are just a review. We learned we can take a primary alcohol and oxidize it using PCC to an aldehyde. We also learned that we can take secondary alcohols and oxidizing it using PCC or chromic acid to make a ketone. We learned that ozonolysis can produce aldehydes or ketones depending on what types of groups are attached to the carbons of the alkenes. So if the alkenes have H's attached, it's going to produce aldehydes. If they have only R groups attached, they will produce ketones. We also learned to produce aldehydes and ketones from alkynes. So using an alkyne and mercuric sulfate as well as sulfuric acid and water, this is going to produce a ketone. We can also use hydroboration oxidation for alkynes using 9-BBN as well as hydrogen peroxide and sodium hydroxide to produce an aldehyde. Again, these are all review from previous chapters. Aldehydes and ketones are capable of having resonance. So with both aldehydes and ketones, we have a carbonyl. A carbonyl is a C double bond O, so we have a pi bond between two atoms with different electronegativities, which is one of the 4 patterns that we were practicing with resonance structures. Now what that means is the pi electrons can come up onto the oxygen atom, and we can create a second resonance structure with a negative charge on oxygen and a positive charge on carbon. So these are the 2 resonance structures that exist for aldehydes and ketones. Now if we consider the hybrid resonance structure, at any given moment we can have a negative charge on the oxygen or a positive charge on the carbon, or they can both be neutral. So the way that we will express the hybrid resonance structure is we will show a partial negative charge on oxygen and a partial positive charge on carbon. Now, what this means is this partial positive charge means that the carbon is electrophilic. So the carbon is susceptible to nucleophilic attack. And that's going to be the basis of all the reactions we see in this chapter. Now, in comparing the reactivity of aldehydes and ketones, we want to consider the different groups attached to the carbonyl. So with the ketone, we have R groups attached. Now, R groups are carbon-containing groups, and we learned in chapter 18 that these R groups can be considered electron-donating groups or weakly activating groups. So what this means is with a ketone, we have a partial positive charge that is going to be stabilized by these R groups donating some of their electron density, similar to what we saw in chapter 18. So these R groups can stabilize this partial positive charge and make it less of a partial positive charge. With an aldehyde, we only have one R group, if any, providing that stabilization. So what this means is that an aldehyde is more susceptible to the nucleophilic attack because the partial positive charge is less stabilized by the R group. So aldehydes in general are more reactive. All of the reactions in this chapter are going to be based on a nucleophilic attack at that carbonyl carbon. Now there's two main types of conditions that most of the reactions will run under. We have basic conditions and acidic conditions. So right now we'll go over the general mechanism that we'll see under basic conditions, and then we'll compare it to the general mechanism we will see with acidic conditions. So for the most part, under basic conditions, the first step in the mechanism will be the attack by the nucleophile. Now for the most part, the nucleophile will contain lone pairs and it will often contain a negative charge. We will see the attack of the carbonyl carbon because we know it is electrophilic with its partial positive charge. That will kick the electrons up onto oxygen. Now at this point, we have a negative charge on the oxygen. A few things can happen and we'll see differences in the mechanisms in the next video, but one of the possibilities is we can protonate this oxygen with a proton source such as water. And this would be the product of a nucleophilic attack under basic conditions. Now in using water, we would produce hydroxide, which is negatively charged. Now with mechanisms under basic conditions, it's very important that we avoid strong acids. So in general, a strong acid would mean H3O+. So we want to make sure to avoid forming or using H3O+ when we are working with a reaction under basic conditions. Under acidic conditions, nucleophilic attack will happen in a different order. Under acidic conditions, we have protons floating around in the solution. So as a result, the oxygen of the aldehyde or ketone will be protonated first. So we will form an intermediate with a positive charge on the oxygen that is actually more susceptible to nucleophilic attack than it would be otherwise. Now at this point, a nucleophile can come in. Now nucleophiles under acidic conditions are usually neutral. There's no negative charge. So our nucleophile will come in and attack the carbon, giving the electrons to the oxygen. So this positive charge is important because a neutral nucleophile is not as nucleophilic as a negatively charged nucleophile that we see under basic conditions. So we're making this intermediate more reactive and more attractive to the neutral nucleophile. Now in the end, the product that we form is similar or exactly the same as the product that we formed in the basic condition mechanism. We just had a slightly different order in terms of the different types of attacks. Now under acidic conditions, we want to make sure to avoid the formation of strong bases. So that means we don't want to see any hydroxide or any negative charges under acidic conditions. Under acidic conditions, you will usually see neutrally charged molecules as well as positively charged molecules. As we will see in the next few videos, there are different types of nucleophiles that can react with aldehydes and ketones. Each of these reactions are going to follow those generic mechanisms that we just took a look at, including the attack of the nucleophile to the carbonyl carbon. So we will be taking a look at reactions involving oxygen nucleophiles, nitrogen nucleophiles, sulfur, hydrogen, and carbon.